Okay, in the next, let us talk about the noise. This is another aspect of uh, of supervised learning. Let's consider the typical problem, which is a simple one, and we revisit that to see is there any extra complexity that might be of interest in terms of learning. The problem is what we have encountered in building the decision trees. That is, given the condition of the weather, the task is to decide whether to go out, do some report, or sorry, do some sport, or stay home. In the original problem definition, we have some deterministic decision to make given the weather condition. But please consider, is that entirely possible that given the same kind of weather conditions, say the overlook is sunny, it is cool, it's a normal humidity, but it with a strong wind. Is that possible that some people in this condition, they would like to go out for some sport, for example, jogging or some whatever, determining the preference of the people and the nature of the sport. And for some other people, given exactly the same condition, they might think it is not suitable, it's rather to decide to stay home, not play. It is not difficult to imagine this is the practical case in many kind of decision making or classification problems. So in the next, we will consider the situation that in the learning problem, the target to be predicted has some stochasticity in it. That is, given some particular x. The target value is stochastic. It's a distribution of possible y values rather than a specific target function we want to approximate. Of course, the previous problem setting is a special case in this more accommodating configuration. That is, when you have a deterministic target function, we can see that the probabilistic distribution of the target value is something like when the target value equals the target function, the deterministic function, the probability is 1 and otherwise 0. There is an alternative view of this configuration, that is, the stochasticity, the randomness can be considered as a noise. That is, there is some target function, and this function does exist, but we do not know. We cannot never observe the true value of this function. It is always present itself with the deterministic function's value plus some noise. In terms of the learning framework, this is the original learning framework. We are concentrating our focus in this part. Previously, we have some distribution on the data space X. And according to this distribution, we have some random samples from the X space with some unknown target function. The function assigns a particular y value, the target value, for each individual X sample, and we will have our training sample set. Now we introduce another piece of randomness, that is, given X, the value of the target is also a probability distribution. Here is a side note. Take care that I have use a capital sample x and y to represent two random variables, while in the previous discussion, I have used a particular a bold-faced lowercase x that refers to a particular value of x. These refers to very similar and sometimes interchangeable concepts, but I'd rather to use random variables to represent concepts in the learning framework. So don't be confused. And if we explicitly write out this data generation process, we have something like this. We have the X distribution working on the data space X, generate X samples. For each of the X sample, the Y value is according to some Y distribution, target distribution, and eventually that gives us when the X value and the target distribution jointly work together, that gives us the observed training samples. Now we have two kinds of randomness, stochasticity, in the learning process. They both contribute to the generation of the observed dataset. They both contribute to the randomness, but there is an important difference we need to keep our mind, and this difference underlies some of very important learning methodologies. The target distribution of y given x is the target for learning. That does not need too much explanation. Previously, we want to learn a target function which is deterministic, which is a special case of the stochastic characterization of y given x. Now we want to learn the distribution of y given x. On the other hand, the input distribution px is not a target for learning. It contributes to learning. It is a very important element as the distribution, which determines the distribution of the data in the entire learning process. But this is not a target of learning. Rather, it provides us a kind of relevance measurement of the learning process. To be specific, it tells us at which points of x the learning should be focused on. So if we change our notion of the target distribution from the random variable y determining on the random variable x into the random variable y determining some specific value of evaluation of the random variable x, we should be focused on those evaluations where the x value is generated by the distribution of x. Let me discuss a very specific example. Say in this class, I want to I want to have a look at some student attributes. Try to predict how well you perform in this subject of data analytics. If my distribution of students are mostly come from senior computer science students, so at the stage you entering this subject, it might be you have already get enough programming training previously, and I, as a lecturer, should not be too much worrying about your programming. So then I might have a good model predicting your performance by looking at your basic mathematical skills, such as the performance in introduction to statistics, linear algebra, stuff like that. But on the other hand, if for some year I have the cohort of students that comes from both computer science and from the science faculty, where we have students with background of biology, with chemistry. Therefore, you can imagine that a model that focuses on the student's previous performance on mathematical skills will have overlooked the student's programming skills when the student comes from a different background, and therefore the predictive effectiveness would not be as good as the model worked on computer science students. And so that is the role that is played by the distribution of X. So the take-home point is, now we consider two folds of stochasticity, the randomness in machine learning. Those two kinds of randomness all contribute to the same random distribution of observed data, but they contribute from two different aspects. For one aspect, the conditional distribution of the target value given the observed data is what we want to learn, and the other aspect determines where in the data space we should be focused our predictive capacity, our modeling efforts.